Welcome to our lecture on magnifying optics. When you finish this lecture, you should be able to describe the magnifier, microscope, and telescope, calculate the magnification of these devices, understand the concept of diffraction limited resolution. Okay, now making things look larger isn't that difficult. You just get closer to them. So closer objects look larger because they have a subtend a larger angle, theta, called the angular size of the object. So here, of course, here's an object when you at a certain distance, and it will subtend a certain angle here. If you move up closer, the angle gets larger. But there is a limit on this, something called your near point. If you get something closer to your eye than your near point, it comes out blurry. And the worst thing about this is also as you age, or if you're farsighted, your near point could be 100 centimeters. It limits to how close you can get something. So in this case, if your near point is 25 centimeters, the maximum angular size viewable by your unaided eye is for h in centimeters, h over 25 centimeters. This will give you theta near point. Now, if your near point is larger than this or smaller, you should substitute in the one that you have. And of course, all this is just this divided by that. Now, notice that this will be in radians, so be careful with that. And also, make sure that h is in centimeters. There's a units trap there. Now, suppose we view an object of height h through a single converging lens. Remember, converging lenses can magnify. Diverging lenses do not, so it must be a converging lens. If the object's distance from the lens is less than the lens's focal length, but very close to the lens's focal length, you're going to see an enlarged upright virtual image. And used in this way, the lens is called a magnifier. So what this lens does, here's the object that would be very difficult for you to examine in good detail. But if you put a magnifier in between you and the object and set it up such that the distance of the object is just inside the lens's focal length, just slightly smaller than the lens's focal length, you will see a magnified virtual image. And because it is magnified, you'll be able to examine it in greater detail. Now, when using a magnifier, your eye will see a virtual image subtending an angle theta equals h over p. If we place the image at a distance I equals infinity, then the object's distance is p is approximately equal to f. So theta will be h over p, or approximately equal to h over f. Angular magnification is the ratio of the apparent size of the object when using a magnifying lens rather than simply looking at the object at your near point. So in other words, magnification equals theta over theta np. Combining these equations, the ones we had on the previous page, as well as these, we will find out that the angular magnification for magnifying glass is m equals 25 centimeters over f. Now, if you're dealing with a near point that's other than 25 centimeters, you might want to change that. Also remember that f has to be in centimeters. This is a ratio. You have to make sure they're both the same units. If you view a bug with a magnifying lens having a 12.5 centimeter focal length, then the lateral magnification is infinity, the angular magnification is 2. Ideally, the image is infinitely tall and infinitely far away, making the lateral magnification infinity, but the image still subtends a finite angle, so the angular magnification is not infinity. It's somewhat less than that. Now for the microscope. Here's a picture of a microscope showing some of its major parts, the eyepiece, which is the piece you look through, the objective lens, which is closest to the object. Notice you have a choice of lenses. This rotates. The focus knob here, which moves the platform up and down. And then there's usually a light under here called an illuminator. And there's a prism in here that will bends the light path so the eyepiece is at a comfortable angle. Now, a microscope can attain a magnification of up to 1,000 times by a two-step magnification process. The specimen to be observed is placed on the stage of the microscope directly beneath the objective. The objective is a converging lens with a relatively short focal length. The objective creates a magnified real image that is further enlarged by the eyepiece. And the choice of magnification is in here. They have different objective lenses. So this is basically a simple ray diagram of a two-lens microscope. The object is placed just outside the focal point of the objective, which creates a highly magnified real image with a lateral magnification of m equals minus I over p. The minus sign just means that the image is inverted. This is the tube length. Here's the focal length of the eyepiece. Here's the focal length of the objective. Here's the object. Here's the focal length of these various lenses here. Now notice that the object's just beyond the focal point of this lens. The magnified image of the objective acts as the object for the eyepiece. And this eyepiece acts as a magnifier and forms an image at infinity that is seen by a relaxed eye. So the lateral magnification of the objective is m objective equals minus I over p. And that's approximately equal to L over f objective, where L is the length of the tube. The objective and eyepiece produce a total angular magnification of m equals m objective mi And that will be equal to minus L over F objective times 25 centimeters divided by FI. You want to be careful with the units on these. Probably should all be centimeters. The minus sign just shows that the image in the microscope is inverted. Most biological microscopes are standardized with a tube length of 160 millimeters. Blood cells through a microscope. A pathologist inspects a sample of 7-micron diameter human blood cells under a microscope. She selects a 40 times objective and a 10 times eyepiece. What size object viewed from 25 centimeters has the same apparent size as a blood cell seen through the microscope? Just as we've done all along, you should always write down the physics, the knowns and unknowns, and the formulas. So the physics is microscope optics. The knowns and unknowns are that magnification of the objective is minus 40. The minus means it's upside down. This is where the 40 comes from. Magnification of the eyepiece is 10. That's where this comes from. The diameter of the cell is 7 microns. D prime is the apparent size in microns, which is what we're looking for. The formula is M equals M objective times MI. And we also know that the absolute value of M is H prime over H or D prime over D. And we find the M is M objective times MI, and that equals D prime over D. So D prime will equal D times M objective MI, where we ignore the signs. So then D prime is 7 microns times 40 times 10, or 2,800 microns, or about 3 millimeters. And this is about the same apparent size as the letter O on a page seen from a comfortable reading distance. Telescope. There are many, many kinds of telescopes. A simple telescope contains a large diameter long focal length objective. It can be either a lens or a mirror that collects parallel rays from a distant object and forms a real inverted image at distance I equals F objective. The focal length of the telescope objective is very nearly the length of the telescope tube. Actually, if you add the sum of the focal length of the objective plus the focal length of the eyepiece, you get the length of the tube. That's the distance that the two lenses are set apart. Now, the eyepiece focal lengths are typically very small. They're like 10 millimeters, 20 millimeters, 30 millimeters, and they're used to set the actual magnification of the telescope. The objective has a very long focal length. The eyepiece functions as a simple magnifier. It has a short focal length. The viewer observes an inverted image. The angular magnification of a telescope is M equals theta objective divided by theta eyepiece, and that equals minus F objective over Fi. And this just means that the image is inverted. Now, here is a simple ray diagram for a refracting telescope. Okay, here's the focal length of the objective. Here's the focal length of the eyepiece. This would be the length of the tube, this plus that. We're looking at parallel rays from a distant object. And that will, of course, come to focus here at the focal length because they're parallel rays. And the eyepiece acts as a magnifier to form an image at infinity that's seen by the relaxed eye. Now, a refracting telescope uses 2 lenses. They are also called a refractor. These are practical only for small sizes, as large lenses are extremely difficult to make and are so heavy they sag under their own weight. On top of that, glass lenses are so heavy they can make the tube sag, and then you have trouble with keeping the optics in alignment. If the optics get out of alignment, then the telescope basically becomes useless. These also suffer from chromatic aberration and can be mainly used only for visible light. Glass blocks other wavelengths. And most of the interesting stuff occurs at the other wavelengths. Now, in reflecting telescopes and in refracting telescopes, bigger is better. The light gathering ability is proportional to the area of the objective with the square of its diameter. So if you double the diameter of a telescope, you have 4 times the light gathering ability. The resolution is also improved with larger diameter objectives. Now, mirrors can be made very large, and they can also be made in segments that can even be adjusted in real time, much as the eye adjusts. Mirrors do not suffer from chromatic aberration, and mirrors can be made from many kinds of light, from radio to gamma rays. The large telescopes are reflectors, and they are generally use a large parabolic mirror. The parabolic mirror is set up to avoid spherical aberration as their objective. There are many kinds of reflectors, and new ones being developed all the time. This one is a Newtonian reflector, and it's named for Isaac Newton. He invented this. Basically, parallel light rays come in. This is the primary mirror. This would be the diameter of the objective. This is the objective right here. And what is the objective? It's the first thing that sees the light. Okay, there's a secondary mirror that's flat and placed at a 45-degree angle. And that sends the image out to the eyepiece, which is right here. Now, people always ask me, does this leave a hole in the image? No, for the same reason that the blind spot in your eye doesn't leave a hole in your eye. The light fills it in. The only thing it does, the image blocks some of the light, so it makes it slightly dimmer. But the telescope takes care of that anyway because it's large. This is relatively small compared to that, so it doesn't block a lot of light. If you increase the diameter of a telescope's objective lens and tube diameter with no other changes the telescope will have, well, this has nothing to do with magnification. The magnification is set by the choice of the eyepiece relative to the focal length of the objective. So we'll have the same magnification, but it will have more light gathering power and better resolution, which is the ability to distinguish between two closely spaced distant objects. For observing light of wavelength lambda nanometers, the smallest separation angle in arc seconds, where 1 arc second is 1 over 3600 degrees, that's 60 times 60 minutes per degree and 60 seconds per minute, or these would be arc minutes and arc seconds. A telescope can resolve is related to the telescope aperture, d in centimeters, by alpha in arc seconds equals 0.0252 lambda in nanometers divided by d in centimeters. Now notice that this is a mixed unit. The units are taken care of in here, but you have to make sure you use the right ones. Now you can see that d is on the bottom. So if you get d big, the largest d you can get, this makes this as small as possible. When this is small, it means that you can distinguish better between two closely spaced objects. This brings us to the topic of resolution of optical instruments. Optical instruments suffer from various types of aberrations. One of them is chromatic aberrations. This would be only for lenses. Okay, lenses are the ones that suffer from chromatic aberration. Any actual glass lens has dispersion. That is, its index of refraction varies slightly with wavelength. And even just slightly is enough to mess this up. Consequently, different colors of light come to focus at slightly different distances from the lens. So you can see what's happened. Red gets bent less, blue gets bent more. So there's a bunch of different focal points for different colors of light. This is called chromatic aberration. And it's the same thing that causes this. Now, this is what it looks like. What you would typically have is rings or color separation here. And by the way, only lenses have chromatic aberration. Spherical aberration can happen to anybody, including mirrors and lenses. Our analysis of thin lenses was based on parallaxical rays traveling nearly parallel to the optical axis. In reality, most of the time they aren't. So what happens is rays incident on the outer edge of the spherical surface are not focused exactly to the same point as rays incident near the center. So the ones that go through the outer edge, have a shorter focal length than the ones that go out through the center. And this is called spherical aberration. And this makes things that look like blurs or rings around light. Now, we want to correct this stuff. And the way we correct aberration in our optical instruments is pretty much the same way we correct aberration on our natural optical instrument, which is our eye. We give our instruments eyeglasses called combination lenses. Combination lenses use lenses of different materials and focal lengths in order to partially correct for chromatic and spherical aberration. Most optical instruments use combination lenses rather than a single lens. Okay, large telescopes use parabolic mirrors to avoid chromatic and spherical aberration. No mirror has chromatic aberration because mirrors are reflectors, not refractors. In order to get chromatic aberration, you have to have a refraction going on. However, mirrors can suffer from spherical aberration. Spherical aberration occurs when the mirror is ground as part of a sphere instead of made out of a parabola. So if you make a mirror out of a parabolic shape, you don't get spherical aberration, or at least you don't get as much of it. That means that all the light coming from hitting at the sides of the mirror will come to the same focal point as the light hitting the center of the mirror. Lenses can suffer from both chromatic and spherical aberration because lenses are refractors. The way to avoid, or at least partially avoid, chromatic and spherical aberration on the lens is to use a compound lens made up of different materials. You pick the materials such as the wavelength dependence of the index of refraction of one material compensates for the wavelength dependence of the index of refraction of the other material. If you pick the materials correctly, grind the lenses carefully, you can have all the different rays of light from the edge of the lens as well as from the center, and have all the different wavelengths of all this light come to pretty close to the same focal point. You can't get it totally correct, but you can come close with proper engineering and proper grinding. All optical instruments, including your eyes, has diffraction aberration caused by the inherent wave nature of light and the fact that light, when it encounters an obstruction, bends around the obstruction. That's called diffraction. And a lens that acts as a circular aperture of diameter d. Consequently, the lens will focus and diffract the wave, both focuses and diffracts the light wave. Light diffracts around any edge it encounters just like any wave. So anything in the light path, including this secondary mirror, including the supports for the secondary mirror, can have diffraction around the edges, because light will bend around the edges, any edges that it encounters, and that causes diffraction aberration and degrades the image. You can't avoid this. The only you can do is try to reduce it as much as possible through proper engineering. A lens or a mirror can be modeled as an aperture, a circular aperture, followed by an ideal lens or mirror. Any circular aperture, just a small hole, produces a diffraction pattern with a bright central maximum surrounded by dimmer fringes. It's what I call a target pattern for obvious reasons. This is the unavoidable consequence of the fact that light is a wave and diffracts around edges, and it limits the ultimate resolution of any instrument that uses electromagnetic radiation. And frankly, just about everything we use uses electromagnetic radiation. It's the ultimate limit. Now, a converging lens will bring the diffraction pattern to focus on the image plate. So here's a converging lens. Here's the wavefront coming in, parallel rays coming in. And notice we have the central maximum. That would be this right here. And then followed by, as you work your way outward, these diffraction rings. So these secondary and tertiary maximas. So the result is a perfect lens focuses parallel light rays not to a perfect point of light, but to a small circular diffraction pattern. And that complicates things. Whether it is a problem or not depends upon how large it is. The bigger it is, the more likely it is to be a problem. The minimum spot size to which a lens can focus light of wavelength lambda is Wmin equals approximately equal to 2 times the focal length times theta 1, or 2.44 lambda f over d. Now this is for a circular aperture. D is the diameter of the circular aperture lens and f is its focal length. In order to resolve 2 points, their angular separation must be greater than theta min, where theta min equals 1.22 lambda over d. This is the lens angular resolution. Now be careful with this, because this is a ratio. Theta min must be in radians, and you have to be very careful with this. This number actually, the reason this isn't 1 is because it's a circular aperture. To focus light with the smallest possible spot, you should choose a lens with, well, if you look at this equation, you want to have the largest diameter, because you want this as small as possible. You want to have the largest diameter, and you want to have the smallest wavelength and a short focal length for your lens. So if you got a choice of wavelengths, use blue light instead of red. Use the shortest focal length you can use, and get the biggest telescope you can afford. Let's do an example. A 12 centimeter diameter telescope has a focal length of 1 meter. What is the diameter of the image of a star in the focal plane if the lens is diffraction limited and if it is in space where Earth's atmosphere is not a limitation? Earthbound telescopes have some serious limitations caused by the Earth's atmosphere. The physics of this is diffraction limited resolution. Most stars are so far away they appear as point objects, not as disks. Since resolution is also wavelength dependent, we will pick lambda equals 700 nanometers as a worst case. We write down the knowns and unknowns with the units. D equals 12 centimeters, F equals 1.0 meters, lambda equals 700 nanometers, and we're looking for a W min. We have a units nightmare here. We want to get all the units to the same units. So the formula would be W min equals 2.44 lambda F over D. So it's 2.44 times 700 times 10 to minus 9 meters times 1 meter divided by 0.12 meters. Ends up being 14 microns. This would not be noticeable to the unnaked eye, but if it was recorded in a large, say you took a picture of it and then blew up the picture, you would have problems with this. And the way we could get around that, the best way would be to increase the diameter of the objective, get a bigger telescope. That would proportionally improve the resolution, and this is why one of the reasons we build telescopes so large. The figure shows 2 distant point sources, object 1 and object 2, being imaged by a lens of diameter d. The images each form a diffraction pattern of alternating bright and dark fringes. Rayleigh's criterion determines how close together the images can be before you can no longer distinguish or resolve them. 2 objects are barely resolvable as separate objects when the maximum of the image from one object falls on the minimum of the image from the other object. If you look here, the maximum from image 1 is falling on the minimum from image 2, or the maximum from image 2 is falling on the minimum from image 1. At that point, this determines theta min, and when the objects are barely resolvable as separate objects, alpha v equals theta min. This is like seeing the light from a distant vehicle approaching you. At first, it looks like one light, and you can't tell if it's a car or motorcycle, or maybe somebody with a burned out headlight. As it gets closer, they slowly begin to resolve until you can see them as separate lights. At this point, they're just barely resolved. That's Rayleigh's criteria. If you look at the two diffraction patterns from the lights, from these two lights, you can see that the maximum from one overlaps the minimum from the other, and the minimum from this one matches the maximum there. At that point, they're barely resolvable. You can tell they're two separate lights. Of course, if they keep on approaching, then you wind up with fully resolved, and it's very easy to tell here. So the angular separation between two distance point sources of light is alpha. Rayleigh's criteria states that the two objects are resolvable if alpha is greater than theta min, where theta min is 1.22 lambda over d. This 1.22 factor is due to the circular shape. If it were slits, it'd be 1, not 1.22. And this, of course, this is if alpha is greater than theta min, you can tell. Now, here is where it's marginally resolved. This is where alpha equals theta min. You can just see that you can kind of tell that there are two. And of course, this is the diffraction pattern right here, the combined one. Here is where alpha is less than theta min. And you can tell, you can't tell for sure. Is this one light or two? For best viewing, you want alpha, you want theta min to be as small as possible. Two distant stars are only marginally resolved when viewed through a telescope having a 10 times eyepiece and a filter that passes only light with a wavelength near 500 nanometers. One better way to resolve the stars would be to view the stars using ultraviolet wavelengths. Now, the other thing you can do is use a telescope with a larger objective. If you look back here for Rayleigh's criteria, you want this to be as small as possible. That means you want the shortest wavelength, largest diameter scope. This is why we use large scopes. We actually covered this before. I'm not going to go into real detail here. This is the resolution of a diffraction grating. But if you look here, here's the resolution is lambda over delta lambda, or n times m, where delta lambda is the difference between two closely resolved, close wavelengths. M is the order number, and n is the number of slits or lines that are illuminated. And notice that you want the large order number. You want the large number of slits. This is why we use gratings instead of double slits. We want n to be as big as possible, and we want m to be as big as possible. Thank you.